Okay, so this is where we left off with our warm up. And we realized we got to a place where analytically we can't calculate this double integral. But I'd like us to picture what it looks like visually. So if you recall, the double integral of a function of two variables can be interpreted as the signed volume of that function over your region R. This picture is totally not going to do justice to it, so let's go ahead and put up an actual picture. Okay, so this is actually what the region looks like, way better of a picture. This is my function z is e to the negative x squared minus y squared, which is a Gaussian. And then this is the semicircle, which is the region I'm integrating over. And so you can see we can interpret this double integral as this volume of this half of the mountain. And we can interpret when we try to integrate in Cartesian coordinates with respect to dy dx that we are chopping up this region into these rectangular boxes along constant x and constant y values. So we can add, let's do more just so we can see. Let's do maybe 20 in both directions. You can notice as we take the limit and add more and more, we're going to get the actual volume underneath this mountain. But analytically, this is not working too well for us to chop up the mountain this way. And so the question is there a more natural coordinate system we could use to chop up a region that looks like this? And if you were thinking, hey, the bottom of the region looks like part of a circle, I'm thinking I should use polar coordinates instead, you are right. So let's talk about what it would look like instead of chopping up for constant x and constant y, if we chop up for constant r and constant theta. So we can make a little picture here. And notice, let's start with way less so you can see what it's going to look like. Let's do 10. Constant r and constant theta is going to give us, I like to call it this polar graph paper, kind of looks like this little spider web shape. But that's going to lead us to these little, I mean, there's still these three-dimensional objects, but they're no longer rectangular. They're kind of like these little curved curved box segments. And we're going to be adding the volume of those up as we chop up this region into more and more of those. So let's see analytically how we can do this. And it's going to turn out to be a much easier way, and actually the only way that we can calculate this particular double integral that we started with on our warm-up. So I'm going to just go back to our notes. These notes are posted on Canvas, and I recommend that you print them out, the blank version, and just follow along as if you were just in class, filling out your notes. Let's see if we can get, there we go. Okay. So a quick review, what are polar coordinates? R is just going to be our signed distance from the origin. I'm saying signed because technically we can define R to be negative, just like we can define X or Y to be negative. And then theta is going to be this angle from the positive x-axis. So recall, how can we relate the two? Let's start Cartesian to polar. We can see from Pythagorean theorem that x squared plus y squared is going to give me r squared. And then we can use some trig to notice that tangent of theta is going to be y over x, assuming x is not 0. We can go the other way, again using some trig, by noticing that cosine of theta is adjacent over hypotenuse x over r, which means that x is r cosine theta. And then similarly, we get y is r sine theta. Okay, so let's start with, let me just draw a really simple region here. Let's look at this part of an annulus. Let's just say this is y equals x. We'll make it kind of straightforward here. And let's let this radius, this one has radius 1, this one has radius 2. And I want to describe just this part in here. Okay, so notice this is going to be the region where my R values are between 1 and 2, and my theta values are between 0 and pi over 4. So this type of region is what we call a polar rectangle, because the bounds are constants for my polar coordinates. And another way you can visualize this polar rectangle idea, over here are my, in polar, these are my polar coordinates, r and theta. And so when I plot what looks like a rectangle in r and theta, the corresponding region in x and y is this kind of curved polar rectangle. It's this curved region that's not rectangular in Cartesian coordinates, but it is what we call a polar rectangle. And so we'll be looking at, in fact, let's look at a nice system like this, or a nice little chunk like this, because when we go to chop up our region of integration, instead of chopping up in rectangles in the xy plane, we're going to be chopping up in these polar rectangles in the xy plane, which will be equivalent to actual rectangles in the r theta plane. And so we need to think about, if we start chopping up our region like this, how is that going to affect the area of a little rectangle? Because if you recall, when we were setting up our double integrals in Cartesian coordinates, we were taking the area of one of our Cartesian rectangles times the height of one of our rectangular boxes. And we're going to do the same thing in 3D as we're integrating over this polar region. It's back here. Remember, we're integrating over this polar region up here. So I need to figure out what's the area of the base and then times the particular height it corresponds to on the mountain. And so that leads us to a great question, is what is the area of one of these blue boxes? And does it depend on both r and theta, or just one of those variables? And so take a moment before we calculate it, and I want you just to imagine, if I change theta, or just notice looking at the picture, if I change theta, does the blue area of the boxes change? Versus if I change in r, does the blue area of the boxes change? Okay, notice the red area of the boxes on the left is not changing in r or theta, but on the right, the blue boxes do change as I move in r, but not as I move in theta. And that is going to be something we see that comes out in our algebra in just a minute. So let's switch back to that.